Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 48. That will be the last lecture of induction motor. I promise the previous one will be last, but this one I promise will be last. So today we will be discussing about the remaining two methods of braking, that is plugging and regenerative braking, and we will discuss about harmonics in induction motor. So already we have discussed that rheostatic braking, right? In rheostatic braking, if you remember, you observe that my slip, right? Slip S prime, the new slip was always something lower than 1, correct? It was 1 minus s was previously 0 0.05, 0.2. So basically previously in dynamic braking or rheostatic braking, basically my slip, right, was in this region, and this region is actually called as the motoring region. Why is it called as a motoring region? Because in this region only my induction motor behaves as a motor, right? When the slip is between 0 to 1, the induction motor actually behaves as an induction motor right? Basically in this region my nr will be less than ns and it will rotate in the same direction. For some reason, if slip is negative, what does that mean? Slip negative, basically, like, what is slip is basically ns minus nr divided by ns. So slip equals to 1 means nr is very equals to nr is ns minus nr is all, sorry, slip is equals to 0 means relative speed is almost negligible, right? If slip is negative, that means this quantity is higher than the synchronous speed, correct? That means the rotor speed will be higher than the synchronous speed. If the rotor speed is higher than the synchronous speed, what does that means? That basically means slip will be negative basically then that means the rotor will rotate at a higher speed than the synchronous speed. When will that happen? That will happen in regenerative braking. Something similar we used to do in DC machines in regenerative braking, right? Same thing we will do here but differently. We'll discuss how can I make the rotor speed higher than the slip speed. You might have the doubt, sir, how can I make the rotor speed higher than the slip speed? Because the rotor always follows the stator rotating magnetic field, right? Rotor will always follow the ns, it will never be able to reach ns, right? How is it possible? So what we'll do, we'll change the number of poles. So we'll we will increase the number of poles. If I increase the number of poles, what will happen? The number of the ns will reduce, because ns is what? 120 f by p. So p is increased, so ns will reduce. So suddenly ns is lower than nr. So what will happen? Slip will be negative, so a negative torque will be developed. Again the same thing, basically my rotor will try to follow the stator magnetic field, stator rotating magnetic field. Now the stator rotating magnetic field is actually lagging behind, right? Rotor is rotating at a faster rate than the stator, so stator is lagging behind, so the stator magnetic field will try to pull the rotor back, okay? That's why the torque is negative beyond s, beyond this position, right? S equal to 0. And in this region torque is still positive, but the rotor itself is rotating in opposite direction, right? So here, right, what does it mean? Here slip is greater than 1. What does slip greater than 1 means? So this value has to be greater than 1, right? Basically then that means ns has to be, sorry, this will go, ns will go there, nr will be here. Yeah, so ns is here, ns will get cancelled, nr is less than 0. That means what? If initially my rotor was rotating in this direction, rotor will rotate in the opposite direction, okay? Rotor will rotate in the opposite direction than the initial direction. Torque, still you are feeling that torque is positive, sir. Says torque is positive, it is not opposing. It is still opposing it, okay? How is it opposing? What does this means? This is known as the braking mode. Actually the three methods of braking mainly operate in three different regions. The dynamic braking operate in motoring mode, the regenerative braking will operate in generating mode, the plugging will operate in this mode, okay? So no one will tell you this, okay? Trust me, no one will tell you this with this clarity. So plugging will operate in this region actually, but still it is called as the braking mode. So everyone assumes that in this region only all the three braking modes operate. No. So in braking mode plugging operates, in motoring mode the dynamic braking operates, in generating mode the regenerative braking operates. Okay. So what you have to understand is that uh, here, right, in this region, always you will see that the developed torque will be opposite to the rotor speed. So in this region, what used to happen, the rotor is rotating in this direction, but stator field is stationary. So the stator is trying to pull it back to make it stationary. So again, the torque developed is in the opposite direction, okay, in this region for dynamic braking. For regenerative braking, what happens, the rotor is rotating much faster than the stator. So stator is still rotating in the same direction, I mean stator magnetic field, okay, stator magnetic field is still rotating in the same direction, but rotor is rotating much faster. Again, same rule of principle, the rotor magnetic field always try to follow the stator magnetic field. So the rotor magnetic field is rotating much faster, so the stator will pull it back. So again, the torque developed is on the backward side. Now let's come to here. Here what is happening, the rotor has reversed, because this is nr equal to 0, this is nr equals to ns, right, this point. So rotor speed has reversed, right? If rotor speed has reversed, that means rotor now is rotating in this direction. Still I am applying three-phase supply only. Still I am applying three-phase supply only. What will be the direction of the developed torque? Rotor field will always try to follow the stator field. So again, the direction of the developed torque will be in this clockwise, but rotor is rotating anti-clockwise. So again, the torque direction is opposite. Okay. So something like this we'll use. So it's not like we can totally reverse the rotor direction. We cannot do it. So what we will do? We will reverse the stator magnetic field. If I reverse the direction of stator magnetic field, suddenly what I will do is my rotor is rotating in this direction, in the clockwise direction. Suddenly what I did, initially my stator magnetic field was rotating in the clockwise, but I did something, I changed something that made the stator magnetic field to go with the same speed but in the anti-clockwise direction. Same rule of thumb, that the rotor magnetic field will follow the stator magnetic field. So basically this will develop a torque in the anti-clockwise direction. So this rule of thumb you should always keep in mind in case of induction motor, right? The most important rule of thumb is the rotor magnetic field will follow the stator magnetic field. Okay, rotor magnetic field will follow the stator magnetic field. Now, how will I reverse the direction of the stator magnetic field? Very simple, right? We know by changing the phase sequence. So basically what used to happen was, initially the phase sequence was somewhat like this, right? This was the windings basically, if you remember. This is the stator winding, roughly I am drawing. So I am providing here, let's say IA current, then here I am providing IB current, here I am providing IC current. So what I will do, I will just interchange this connection, just interchange, right? So the coils will remain same. This will be A dash, this is dot, this is dot, this is dot, this is C dash, this is B dash. Okay. So what I will do is, I will just simply interchange the direction, right? So now this will be providing my IB and this will be provided my IC. So what is happening actually, the phase sequence has changed. Previously basically first A was coming, then B was coming, then C, right? This, so again here A is coming, first the peak of A will come, but now the peak of B will come in this direction, right? Like what is the phase sequence? Phase sequence basically means whose peak comes first. So generally ABC is the general like phase sequence of the supply, that we know, right? But when is the peak happening in the flux? Because flux depends on the how the windings are distributed. So first the peak of this winding will come, right? Then the peak of B, IB is flowing in this winding, right? Second winding. So this will come then third. Here what was happening, this was coming first, then IB was coming, then IC. So basically if you see, this was providing a clockwise rotating field, this is providing anti-clockwise. Just that simple, right? So basically now ns has reversed. Can you tell me what will be the new slip s prime? It's very easy, right? What is s slip? Slip is basically, what is slip? Slip is basically the relative speed between the relative speed between stator magnetic field and rotor magnetic field. So divided by the synchronous speed basically. So now what is the relative speed? Now the instant that I reversed my supplies, ns has changed to this direction, ns in the anti-clockwise direction. nr, rotor is still rotating due to inertia in the clockwise direction. So what is the relative speed? Very simple, right? Both are opposite. So relative speed will be added. So the torque developed will be very high now because relative speed is very high. So the frequency of induced EMF will be also very high. Okay. So this will be equals to ns plus nr divided by, this is s prime, okay, divided by ns. Now remember one thing, what was the previous slip? Because I want to write in terms of the previous slip. So this is only one thing that you have to remember, that what was the previous slip? Previous slip was ns minus nr divided by ns. So from here I can easily write what is my, this will be 1 minus ns nr by ns, correct? So basically I can say nr by ns is basically equals to 1 minus s, right? So I can write here, this will be 1 plus nr by ns, so it is 1 minus s, right? So I can replace this, I'm just simply replacing this. So here, right, my nr by ns is simply 1 minus s. That is what I'm doing. I'm replacing nr by ns with 1 minus s. I'm dividing this by ns, right? So that is my s prime, the new slip. So basically the new slip will become 2 minus s. That's it. The slip will become 2 minus s. Basically whatever this graph, right? Whatever was this graph here, all of this will be coming over here in this region. Okay. So the slip will become 2 minus s. That's it. You don't have to worry about anything else. The slip for plugging will become 2 minus s. That is what you have to understand. So let's now solve, like same thing is written over here by changing the phase sequence and all those things. Torque direction will be reversed. So like one important fact, as I have already mentioned, that in dynamic braking what happens, the synchronous speed is 0 because there is no rotating magnetic field. Slip is between 0 to 1. In plugging, the synchronous speed becomes negative, minus ns. Previously it was going in the clockwise, now it will go in the anti-clockwise. So the slip will become 2 minus s. Very simple to understand, right? Here also I have written the same thing only. Okay. So now let's solve the same question, right? Same question as the previous question only, but here we have to calculate the initial braking torque after plugging, right? So basically the first part will be same, right? The calculation of the current, the calculation of the load torque, that will not change because the circuit itself has not changed. So I'll copy and paste this thing. Okay, I'll copy and paste this thing. And this also, right? Basically whatever the value that was coming, this value will be same. Okay, this developed torque, load torque 129.75, this will be same only. This will not change because data is same. I have not changed anything. What will change now? The developed torque, right? Basically now the circuit, right, will change. Circuit will become 2 minus s. So instead of it becoming, this will be s prime, and s prime is 2 minus s. So this will be 0.03 divided by 2 minus s, that is 1.9. This will be even lower actually. But what will be the current? That also we have to find out, right? Yeah. Okay, voltage is still the same. Voltage will not change because supply is still there, right? Per phase equivalent is still there. But what is 2 minus s? That is what I have to find out, right? 2 minus s. So this is 0.3, 2 minus 0.05. Okay. So what will be the current in this case? I want to calculate the current here. So current, right, I2 will be equals to 400 divided by root 3 divided by this okay, this if I calculate, this will be 0.15 something. Let me quickly calculate this. 0.3 divided by 1.95, 0.15 plus 0.5, this wholes, let me write this, right, this will be 0.654 whole square plus the whatever the inductance is there, so 2.4 whole square whole under root will be the current basically. If I know the current, I will be able to find out the torque basically. So this square plus 2.4 whole square whole under root into 400 divided by root 3. So the current is coming out to be actually pretty high. How is it coming out this high? That is what I'm not able to understand. 400, how is it coming out to be more? Okay, sorry, this, right? Okay, divide by 6.187. Yeah, it should be 92.85 amperes. Okay, so now what will be the torque? What will be the plugging torque, right? Remember, load is already there. What will be the torque provided by the due to the plugging? Due to the plugging, it will be 3 by omega s into I2 square into R2 divided by 2 minus s, because the slip has changed now, because the relative speed has changed. So slip is dependent on the relative speed, remember, right? So 2 minus s, so this will be 3. What is omega s? Omega s will be 4p, like basically it will be pi into 50, right? 50 pi, because 4 will get cancelled. It is a 4 pole machine, correct? It's a 4 pole machine, yeah. So into I2 square, that is 92.85 whole square into R2 divided by 2 minus s, that is 1.95, okay, whole square into 0.3 divided by 1.95. This comes out to be quite a lot. What is happening? Okay, into 3 divided by pi into 50, yeah, 25.33. So this roughly comes out to be 25.33 Newton meter. So what are they asking? They're asking me the resultant torque, right? Remember, initial braking torque. If nothing is mentioned, that means they're asking me the overall torque. So overall torque will be summation of both the plugging torque, braking torque will be the summation of the plugging torque plus the what do you call, load torque, right? Or the previous torque. So this will be 25.33 plus 129.75. So it will be 155 point approximately 155 Newton meter. So this will be the braking torque generated at the during the braking initial. Okay, after that what will happen? Obviously torque is there, speed will reduce, so the slip also will increase because the lag will increase. So what will happen? Sorry, slip will reduce because the relative speed will reduce. Yeah, because NR is reducing, right? Yeah, slip will reduce, basically this overall slip will reduce. So what will happen? The rotor will come to rest basically. Okay, so this is the answer for this question. This is the initial torque. Of course, after this something will happen. We don't care about that. We just want to calculate the initial torque. Okay. Now let's understand the this braking, regenerative braking. What is regenerative braking? So let's see this. So regenerative braking can only be possible on squirrel cage induction motor. Why it can be possible on squirrel cage induction motor? Because in squirrel cage induction motor we have the provision to change the number of poles. Okay, just like in wound rotor we have the provision to add the rotor resistance. In squirrel cage induction motor we have the provision to change the number of poles. P will become P dash, right? In wound rotor we can't do it, because in the wound rotor the windings are fixed. If the windings are fixed in the stator side, the number of poles are fixed. In in squirrel cage, the windings kind of, we don't place the windings, right? Current makes its own path, so that is not fixed. That's why it is possible to provide like different poles, change the number of poles. Okay, so this we have discussed under normal motoring mode. Nr will be less than ns. In generating mode, Nr will become higher than ns, just as I have explained in the starting of this lecture. So the slip will become negative, right? Slip will become negative. The torque will be negative, because always the key point is the rotor field will try to follow the stator field. So stator field is lagging, rotor field is moving much faster. So the rotor field will see that and it will try to bring the rotor backwards, right? So in this, right, we cannot make the speed to 0. We cannot bring the speed to 0. So what will happen is that this is the torque speed graph with number of poles equals to P. Let's say if I increase the number of poles, if I double the number of poles, then what will happen? Then the ns will half, right? Ns will become half. If ns becomes half, this point, right, will be shifted here. Then the torque speed graph for that ns will be something like this. If I make it even halfer, it will be something like this. Okay, so what is happening is, ultimately, if this was my stable point, this is the load torque, I will come back here. This will be my stable point, right? Because the torque speed characteristics of the graph has changed. So now I will come back here, correct? So we cannot, like, we can keep on increasing the number of poles, but actually, to be honest, we cannot go to 0 speeds. So with regenerative braking, what do? We reduce the number of poles. So what happens? As the torque developer is opposite, so now the rotor will act as a generator. Rotor will act as a generator. So current will be provided, current will be induced in the stator windings, because the rotor is leading, so it will provide a current to the stator windings that will supply the supply. Basically, supply has to receive the amount of energy. Why? Because you have to understand, the rotor has more energy now, because rotor is rotating at a higher speed than the synchronous speed. So rotor has more energy. So rotor is more powerful. So rotor can, if it wants, it can supply to the stator side. So that is what is we will understand. So this mode occurs when the rotor speed exceeds the synchronous speed, typically due to either external prime mover, or we can change the number of poles by increasing the number of poles. This also can be done. Okay, so yeah, one more thing. By default, if nothing is mentioned, assume that the braking time is plugging, right? If nothing is mentioned, you will assume that it is a plugging type braking. And in wound rotor, we cannot use this, because wound rotor is designed specifically for fixed number of poles. Okay, so here induction motor behaves as an asynchronous generator. Why asynchronous? Because the speed is not ns, right? It is not, nr is not equals to ns. So in synchronous generator, the generator should rotate with a constant speed. That we will study in the next chapter. But in this, it will behave as it is generating. It will behave, because what is happening basically is that initially my stable point was this, right? But the graph has changed now for pole equals to 8. So currently, basically, this is my nr. So with respect to this nr, this should be the amount of developed torque, that is negative. So basically, what will happen? It is negative, hence the rotor will decelerate, come back. Again, this will be my stable point. Okay, so previously the rotor speed was this, now the rotor speed has reduced to this. Okay, so basically rotor speed has reduced to this. So what I can comment? I can comment that basically I can comment basically yeah, so this, right, whatever it did, this deceleration, this is some energy. Okay, if I integrate this area, because this is power, right? Torque into omega is power, omega into t is power, right? This is omega, this is speed, right? So if I integrate this area, this is coming out to a negative area with respect to rotor. That means the rotor is supplying to the stator side. Okay, previously, if this is the graph, right, initially the rotor speed was 0. So if I totally integrated this area, this would have given me energy basically, and this is the amount of energy that the rotor required to reach to this stable point. Now again, if I integrate, although this, don't worry, this will not be required, this will not come in your examination, just I'm giving you a intuition that if I integrate, right, you're observing the actual graph is this now. So it is something negative area. Negative means opposite. Previously the stator was supplying the rotor, so the area was positive. Now it is negative, that means the rotor is supplying the stator. So mathematically also you can understand how the rotor is supplying the stator. Just wanted to give you a induction. So here, right, it does not stop totally. It will not stop. Okay. So this will be ns by 2, and here the synchronous speed will be ns only. Okay. So that is the thing basically. So but the supply system must be capable of absorbing this regenerated power, else we will not be able to use this. Okay. It is used in variable frequency drives or systems in which regenerative inverters are used to utilize the power feedback. So these are the three operating modes. Plugging is this region. Regenerative braking is when nr is greater than ns. So this is the when the slip is basically negative. This is the region where my slip is between 0 and 1, and this is the region where my slip is greater than 1. Okay. So I hope you have understood this basic point, in which region, and in this region we, sorry, this is the motoring region, right? Sorry, this is the motoring region. So in motoring region the slip will be between 0 to 1, and in plugging region the slip will be greater than 1. Okay. So this is also known as the dynamic braking region. Dynamic braking. Okay. So let's do a basic question in gate. Trust me, basic questions only will come, difficult questions will not come. Okay. So we have a 4-pole induction machine. So number of poles is 4, working as an induction generator. So it is working as a generator. So my, first of all they have given me it is working as a generator. So nr has to be greater than ns. The generator supply frequency is 60 hertz. Okay. The rotor current frequency is 5 hertz, right? Rotor current frequency is 5 hertz. So basically fr is 5. And what is the formula for fr? The formula for fr is, if you know, it is s into f, right? This we already know. What is the mechanical speed of the rotor? Now it is operating as a generator. So what will be the slip now? Remember, what is the slip now? So will it be simply equals to s into f? Because they are asking me the mechanical speed of the rotor, right? So remember, if you ever tend to get confused, right, you write fr equals to 5 hertz and you write the basic formula. In normal motoring mode, we know it is equals to sf. You write this equals to, what is s? S is ns minus nr, right, divided by ns into f. What is f by ns? F by ns is basically equals to, okay, they have given me the supply frequency as well. What is f by ns? If you remember, 120 f by p was equals to ns. So f by ns will be 120 f by p was equals to ns. So yeah, f by ns will be equals to p by 120. So this will be p by 120, and here, right, it is what? It is relative speed basically between the stator magnetic field and the rotor magnetic field. Now tell me, what is the speed, relative speed between the stator and the rotor magnetic field? Now the rotor frequency is 5 hertz. Okay. So if my rotor is with nr, okay, and stator is rotating with ns, right? So what is the relative speed? Stator field is rotating with ns. So what is the relative speed between the rotor and the stator field? Still it is nr minus ns only, but the difference is that this time my nr will be higher than the ns. That is the only difference into whatever this value. So this was for the normal operating mode. This formula is always valid. This formula is always valid. Basically it tells us that the frequency of the induced EMF will be depending on the relative motion into divided by the poles. This will be always valid. Okay, into 120 divided by the number of poles, that is 4. So somehow I have made the rotor speed to be higher. I don't know how, but somehow I have, right? So what was the synchronous speed in the previous case? Ns, right? So ns will be 120 f by p in the previous case. So it is 120 into f. F is 60 divided by p, that is 4, that is 30. So that is 1800 rpm. Okay, so this will be basically, this is nr minus ns, that is 1800 rpm into have I done anything wrong? 120 f by p, right? It is 120 f by p equals to ns. So sorry, I'm really excused. Oh, it is p by 120 only, correct only, yeah. Sorry, so okay, sorry, f by, sorry, this will be opposite, right? I've written it opposite actually, other way around. So this will be p by 120. So basically, right here, right, I have just replaced this, so I was wrong. This will be p by 120, sorry. So that's why if you remember fundamentals, even though your formula is wrong, still you will be able to figure it out. So this will be divided by 30, and here this is basically 5 hertz. Okay, so here I can this will be 150 equals to nr minus 1800. So your nr comes out to be, nr will come out to be 1950 rpm. Okay, so this is what your nr will come out to be. So 1950 will be the answer for this question. So many students will get confused in this, how it is 1950. First of all, it should be greater than ns, that is clear, right? Because then only regenerative braking will happen, otherwise regenerative braking will not happen. That is the point 1. Now the point 2 is uh, how do you find out ns? Ns you can find out from the previous formula, and in the new case always you go with the fundamentals. If you ever tend to forget this, remember what is the rotor frequency in normal motoring mode, then from there you derive it general expression. General expression is this: relative speed into the number of poles divided by 120. This is the general expression, this will always be valid. Now you replace it, from here you can find out the value of nr. Okay, so these questions, these kind of questions will come in gate, and these are easier side, these are very easy. Like those difficult questions which we just did will not come in. Okay, very rare chance, but I'm preparing you for the worst, but generally those will not come. Okay, so now let's solve the next one. This is again another interesting question that I can feel like this can come right in the examination. So we have a 400 volt 50 hertz 50 hertz 2 pole induction motor. Okay, 3 phase 2 pole induction motor. It is star connected, so the stator windings are star connected. Squirrel cage induction motor, squirrel cage. Okay, so squirrel cage, what can happen? The number of poles can change. Okay, for on the rotor side. So the slip is 0.05. Dynamic braking is suddenly applied by connecting a DC supply to the stator windings with the positive terminal connected to one end of the windings and the neutral point shorted to the negative terminal. So basically what they're telling me, that I am applying dynamic braking so that the positive side, positive terminal of the DC supply is connected to the one end. Basically all the dots will be connected to the positive side. Okay, and all the neutrals will be shorted and they will be connected to the negative side. So basically if I say you what will be the current direction, so this will be IDC current direction. Okay, because across all of them the same potential is getting applied, right? Same VDC is getting applied. So all of them same current will flow. So VDC is getting applied across all of them. So IDC will flow here, IDC will flow here, IDC will flow here. Okay, so now what are they telling me? They are asking me determine the frequency of the induced EMF in the rotor immediately after the DC supply is applied. So what is the frequency of the induced EMF in the rotor? How will I determine the frequency of the induced EMF of the rotor? Okay, so to determine that, what do you need? FR. What is it? It is, we had just derived the formula, it is relative speed between stator magnetic field and rotor. divided by 120 into the number of poles. Okay. Now you will say, sir, what was the previous relative speed, or what was the previous NR? What was the previous NS? NS was equals to 120 F by P, right? So 120, frequency is 50, number of poles is 2. So NS comes out to be 3000 RPM. NS comes out to be 3000 RPM. Okay. So what is NR? NR will be 1 minus S into NS, right? So it will be 0.95 into 3000. So 3000 into 0.95. So this will be 2850. So you will say, sir, as we have applied dynamic braking, so sir, what will happen is that relative speed between the stator magnetic field speed will become 0, ns dash will become 0, and rotor will still, like, just at that instant rotor will still rotate with speed nr. So your fr, right, will become nr into nr divided by 120 into p. So you will say, sir, this will be 2850 into 120 into the number of poles, that is 2. So here this will, you will say this will be sorry, divided by 3, so divided by 60, right, 60. So this will come out to be 47.5 Hz, and you will be wrong, because remember, number of poles also can change. Okay, number of poles on the stator side also can change, right? This, what is p? P is the number of poles on the stator. So remember this formula here, right, we derived. P is the number of poles of the stator. So in the previous case, as we were supplying, so we wounded the winding such that the number of poles is 4 only. Okay, but remember here the number of poles can change. How? Let me draw it out for you. So if I draw the windings, right, I am observing for, like, how will the windings be distributed. So I have this, actually they should have provided the winding diagram as well, that is a fault on their behalf, but I will still draw it here. So let me copy this diagram. So basically, if I see, for all of these cases, right, current is entering the dot. Okay, for all of them, A dash, B dash, C dash, current is always entering the dot, right? So this is my A, this is my B, this is my C. So current is entering the dot. So I will assume that the dot current entering the dot is dot. Okay, so this will be dot, A will be dot, B will be dot, C will be dot, and the other end will be cross. This will be cross, this will be cross, this will be cross, this will be cross. That's it, right? 3 cross. Okay, so now one thing you observe, one thing you notice, what is the direction of pole? What is the direction of pole? So if I see that the pole, right, pole, this two combined will make a pole, like in this direction, correct? This two combined, sorry, these two combined will make a pole in this direction, in the top. So basically here a north pole and south pole will be created, n1 s1, and these two also will create a north pole south pole, right? So because this is dot and this is cross, yeah, this is okay, sorry. So the axis of the north and south pole of these windings, right, will be somewhat like this. So their axis will be somewhere around here. This will be the south pole, this will be the north pole, and these two windings together will create another north and south pole, right? So basically what is happening, these two are creating a north poles, these two windings are creating a north pole south pole like this. But if I curl my fingers, these are creating a north pole south pole. These two also are creating a north pole south pole, right? Because here I have cross, here I have dot. So again, if I curl my fingers in this direction, left hand side, right? Curl your fingers for this one. Okay, this is going inwards, this is coming outwards. So if I curl, it is going on the left hand side. So these two also are creating a north pole and south pole. It is left hand side, right? Going left. So it will originate from here, N2, it will go here. So same, these two also will create a north pole, south pole. Again, curl my fingers, it is going downwards. So like you will observe that for each of the adjacent windings, each of them are creating a pole. So basically the number of poles in this case becomes 6 now. Okay, just have to be careful. The number of poles in this case becomes 6. Actually it would have been more better if they would have provided the diagram as well. Okay, actually the question would have been more accurate if diagram was provided, right? If diagram is not provided, then the question kind of becomes irrelevant. So this diagram and the winding diagram should also be provided. Okay, that was a mistake on my behalf. So now the pole becomes 6. So if the pole becomes 6, now I can use the formula. Now again I will use the same formula. It will be equals to, my FR will be NR divided by 120 into pole. Into pole. So NR is what? NR is basically 2850 divided by 120. Now the pole has become 6. So the frequency also will increase, right? So that is what you have to be careful about. Okay, 120, yeah. Am I correct here? Yes. So this is 6. Yeah, okay. So let me calculate this value. So 2850 divided by 20, this comes out to be 142.5. Okay, so this will be the actual answer. The previous one will not be the answer. Just be careful regarding that. Okay, because the number of poles can change. Okay, so now let's discuss about the harmonics in induction motors. So mainly actually we will be discussing about harmonics. So there are two kinds of harmonics. One is time harmonics, another one is space harmonics. So in the first part we will be discussing about time harmonics. What does time harmonics mean? So time harmonics, it basically means that harmonics are present in supply current. Okay, so harmonics are present in supply current. So now what happens if harmonics are present in the supply current? First of all, like I will tell you what the harmonics, like due to which things harmonics can come. Okay, I will tell you, but somehow you try to understand this, that harmonics are present in the supply current. So what will happen? So what will be the uh, phase B and phase C currents? Okay, this is the phase A current. If harmonics are there, what will happen to the phase B and phase C? So we know in the phase B, my IB, the fundamental will be very simple. IM, it will lag by 120. So no issues with that. But for the third harmonic, right, what will happen? We had previously also discussed something like this. It will be 3 into omega t minus 120. So it will be basically 3 omega t minus 360, right? Similarly, it will go on. Here it will be IM5 cos of 5 into omega t minus 120. Okay, I am 7 cos of 7 omega t minus 120. So this will be equals to I am cos of omega t minus 120 plus I am 3 omega t minus 360. It will be basically 0 only, right? Minus 360 is nothing but 0 degree only. So I can directly write it 0 only plus I am 5 cos of 5 omega t minus 600. So what is minus 600 basically? So minus 600, okay, let me keep it minus 600 only. Later on we will discuss. So plus I am 7 cos of 7 omega t minus 840 degrees. degrees. Okay, so what will happen to the, this is the B phase current, what will happen to the C phase current? Similarly, just it will be what, omega t plus 120, instead of minus 120 it will be omega t plus 120. So in plus 120 what will happen, just the negative sign will be replaced with positive sign, that's it, right? Negative sign will be replaced with positive sign. So here we have plus, here we will have, this will be 0 only because plus 360 minus 360 is 0 degrees, right? I am rotating a whole circle. This will be plus 600, this will be plus 840. Okay, so yeah, so these are the values now. So let us discuss the effect. What will be the effect? So let me draw a table. Okay, so these are my three phase current. So previously whatever expressions we derived was with respect to the fundamental component. This was omega t minus 120, omega t plus 120. But we had not discussed what will happen if the supply current itself will have harmonics. So in reality, both harmonics, both type of harmonics will be present, time and space harmonics in reality. Okay, but here we are just observing what will happen due to time harmonics. So basically I have the three phase windings, right? Three phase windings are here. Okay, so this will be dot dot and dot, then I will have IA, IB, and let me write it this IB and IC. Okay, so we'll have IB, IA and IC, right? So basically what I can say is so due to the fundamental component I will get a rotating magnetic field, let's assume in the clockwise direction, right, due to the fundamental component, because the phase B current was lagging by phase A minus 120. That's the reason. That's why the peak of phase A will come, then the peak of phase B will come, then the peak of phase C will come, right? So if I just take the fundamental component waveforms, right? Just copy the fundamental waveform. Where is the, okay, I think it's in the previous lecture. Somewhere I had drawn the three phase waveform. Where is it? It's yeah, here. So this was drawn with respect to the fundamental component, right? Now I will draw it for the other components. What will happen to the other components? So if A phase was coming first, then the B phase was coming, and then the C phase was coming. Due to that, I was able to generate a magnetic field in the clockwise direction, right? this was for the fundamental component. Now I will draw the same graph for the third harmonic. So for the third harmonic, observe that all of them are in the same phase, right? 3 omega t, this is also 3 omega t, this is also 3 omega t. So for third harmonic, I don't need to draw any graph, okay, because they are in the same phase. So basically, I can say for the first harmonic, I observe for the first harmonic, first phase A is coming, then phase B is in the clockwise direction because phase B lags by 120 degrees, then the phase C comes. For the third harmonic, phase A is also in this direction, phase B also will be in the same direction, phase C also will be in the same direction because they don't have any phasor difference between them. Now, now let me plot the fifth, because second and fourth harmonics, they generally they don't come and they will not produce uh, like a rotating magnetic field. So because only even odd harmonics come in Fourier series, you will understand why odd harmonics will be present. Okay, so yeah, so basically what is happening with the phase 5 omega t component, that is the fifth harmonic. So if I see here, it is 0 degree. So here it is how much degree actually? This is minus 600. So can I convert this to something else? So if I add plus 720, this will be what? Plus 120, right? Because adding plus 360, subtracting plus minus 360 does not make any difference, right? Adding, subtracting 360 is same. So this will be plus 720, this will be plus 120. So here again, if I subtract 720, does not matter, this will be minus 120, right? Adding 360, subtracting 360 is same with angle. I'm just rotating a whole circle, right? So this is plus, this is minus, right? So basically the 5 omega t component is leads, the phase B current leads the phase A current by 120. So here actually for the fifth harmonic component, phase A is here. So phase B actually will lead. So I will go in the anti-clockwise direction. So this will be the phase B component here, and this will be the phase C component. Phase C will lag. If you see, minus 120 is there. What do you understand? So the fifth harmonic actually is generating a magnetic field. Fifth harmonic is also generating a rotating magnetic field because it is like a balance supply only. Plus 120, minus 120, phase shift is 120, right? But it is rotating in the opposite direction to the fundamental component. So what will happen? So basically it is opposing the actual fundamental magnetic field. That is a bad thing for us, right? That is kind of a bad thing for us, okay? Because we are not able to like get the full magnitude of the flux, right? Because it is opposing. Let's plot it for the seventh harmonic. For the seventh harmonic, like there can be more harmonics as well, okay, obviously there will be, but the magnitude will keep on reducing. You will understand this in Fourier series, okay? So as the harmonic number is increased, so the magnitude of the this amplitude of the harmonic also will keep on reducing, right? So in 7 omega t, seventh harmonic, what is happening here, right? If I again add plus 720, so this will be minus 120 basically, and here if I subtract 720, this will be plus 120. So it is almost similar, like here I have 0 degree phase difference, this is minus 120 plus 120, right? So it is almost similar to clockwise rotation, because here also the fundamental, it was 0 degree, this was minus 120, this was plus 120. So 0 degree, minus 120, plus 120, okay? So this will be 0 degree, minus 120, plus 120. Okay, ABC. So it is also generating a magnetic field that is rotating in the clockwise direction, okay, with speed basically ns. What will be the speed here? What will be the speed here actually? Remember, what is the frequency? Frequency is not omega t. So this speed, right? Yes, it is opposing the main magnetic flux, but it is rotating with a different speed, because what is the frequency here? The frequency is basically 5f, right? Frequency is 5f. So ns will be what? Ns will be ns by 5. Why? Because the number of poles is same, correct? Or effectively the number of poles changes basically. So what will happen if I want to write the ns5, right? What will be ns5? ns5 will be 120 f by p. Okay, so what is happening? So here f, right, is f5, fifth harmonic frequency. What is the fifth harmonic frequency? Fifth harmonic is what? 5 times the actual value. So this will become 120 into 5 into f by p. So this will be basically what is this 120 f by p is what? The actual slip, right? Sorry, actual synchronous speed. So it will be 5 times. Sorry, I was wrong. This will not be divided by 5. This will be 5 times the synchronous speed. So it will generate a rotating magnetic field whose amplitude will be much lower than the first harmony, that is fundamental component, but it will rotate in the opposite direction to the fundamental component with a speed of 5 ns. Same for here, it will rotate in the same clockwise direction with a speed of 7 ns. So the basically the what is happening, the we are getting magnetic fields in weird directions which is not required, right? So what it will try to do, so basically we know rotor always tries to follow the stator magnetic field. So the fundamental component of the stator is telling it to follow with a speed of ns. The third harmonic is not telling it anything, okay, so it is just stationary. Okay, the fifth harmonic is telling that the rotor should follow this fifth harmonic component in the anti-clockwise direction. So the rotor will try to rotate in the anti-clockwise direction with a speed of 5 ns. Okay, and in case of seventh harmonic, it follows in the clockwise direction. The rotor follows in the clockwise direction with a speed of 7 ns, right? So basically what will happen, the rotor is actually wants to rotate in the clockwise direction only, but there will be bit of backward forward movement. So that is, these kinds of movement are called crawling. Okay, so rotor kinds of crawls, right? Or sometimes cogging and crawling, like these harmonics are there. Actually it is not exactly cogging or crawling, but due to these harmonics what will happen, it will basically, the rotor rotation won't be smooth. Okay, so that's why we generally don't want harmonics on the supply end, right? That's why we avoid it, but of course you cannot totally avoid it. There will always be harmonics. Okay, so harmonics distort the ideal sinusoidal waveform, and they can arise due to the following reason. Slotting, like slotting means like you have the slots here, right? So that I will show as well. Like I can show it theoretically, I cannot prove it to mathematically. So sometimes what will happen is the windings are properly not slotted there. Okay, maybe this winding is missing or something. Due to that thing, properly field waveform will not be generated, or it will not ask for the balance supply current. So due to that there can be harmonics, and of course this we have already discussed in transformer, that if core is saturated there can be harmonics. Okay, but as this is air core, so chances of saturation are very low. Okay, and if the supply voltage itself is non-sinusoidal, then how can you expect a sinusoidal current? Okay, that, like, this is a very valid reason, and obviously supply voltage will have some will have some harmonics. Okay, it will not be purely sinusoidal, it will always be the case. You cannot totally generate a pure sinusoidal wave. Okay, so as I have discussed that they are classified into space and time harmonics. Time harmonics we have already discussed, that generated due to non sinusoidal supply voltages. Okay, so time harmonics are generated due to non-supply voltages, and the other two reasons, right, these are generated like these will fall under the category of space harmonics. Okay, so the fundamental component will produce a main rotating magnetic field like this, But the triple N harmonics like third harmonic, ninth harmonic, 12th harmonic, all this will provide a zero sequence current, so they will not produce any rotating magnetic field. It is just like a what, dynamic braking, just like dynamic braking, right? So third harmonic actually is telling it to brake dynamically, stop. Okay, third harmonic, so it is just like dynamic braking. So what we can do with the star, right, with the star, if I connect a neutral, so there is a possibility that the third harmonic can flow through the neutral. Okay, that possibility is there. So that's why uh, tends to circulate neutral in the neutral if present. So all of the third harmonic current can flow through the neutral itself. Okay, that is a possibility. Now, okay, am I correct here? Tends to, because okay, if this, oh no, sorry. Basically, what will happen is, let's say the supply is connected like this, right? ABC, ABC. Okay, but if in the neutral side, okay, if both of the neutrals are connected for the supply and the load side, then the harmonic will flow through the neutral. If one of the neutral is open, then the harmonic will flow through the winding only. Okay, this we already had discussed in transformer, so I'm not discussing it over here again. Okay, now let's come to the fifth harmonic. So we saw for the fifth harmonic we were getting a rotating magnetic field, but it was rotating in the opposite direction to the fundamental component. So it will be similar to 6m minus 1. So fifth harmonic, then m, like m basically means any integer, right? M basically means any positive integer. So m equal to 1, it means 5, then m equal to 2 is 11. So fifth harmonic, 11th harmonic, then m equals to 3 is 17th harmonic. All these harmonics will provide a rotating magnetic field in the in the opposite direction to the fundamental. Okay, so this will provide torque pulsations, heatings and vibrations. Why? Because the fundamental component is telling it to rotate in the clockwise direction, but the fifth harmonic is telling it to rotate it with 5 ns speed in the anti-clockwise direction. But of course the torque produced will be much smaller, because the current due to the fifth harmonic magnitude, right, of the fifth harmonic will be much smaller, right, much smaller than the fundamental component. That is understandable, but still there will be a bit of backward torque, right? So due to that there can be pulsations, there can be heating, vibrations, all those things will be present over there. Okay, now again, triple harmonic already, okay, triple harmonic already we have discussed, fifth harmonic already we have discussed, so only the seventh harmonic is left. So seventh harmonic is there, so we can actually keep it in the one. Okay, let me keep it here only. So seventh harmonic produces a rotating magnetic field in the same direction as the fundamental, okay, but at different synchronous speed. So it will provide a synchronous speed of 7 ns, right? So all these, right, 6m plus 1, basically m can be any integer, positive integer. So m equal to 1 is 7, m equal to 2 is 13, m equals to 3 is 19. All those values of m, right? Basically what will happen? It will produce a magnetic field in the same direction. So actually the torque speed, right, this actually graph is wrong. So kind of what is happening is this torque graph is gone. So what is happening? This was speed, this torque graph was with a speed of ns. So if the magnitude of the torque is lower, because of course the current magnitude of the current for the other harmonics will be lower, but the speed has increased, so I will have more bandwidth basically. So basically the graph, right, if I shift the graph, it will be somewhat like this. Okay, this will be, let's say, for the seventh harmonic, 7 ns, right, because the seventh harmonic and the fundamental component, both of them will provide torque in the same direction, but the fifth harmonic will provide a torque in opposite direction. Okay, so it will be just a mirror image, but the expanded graph, right, graph will be a bit expanded because the speed is 5 ns. Of course it is not up to scale, the graph is not up to scale. Okay. So yeah, so if I now uh, like write the overall torque, so what will be the overall torque? So overall torque will be the summation of these three, right? So initially what is happening, this is like, this is low, this will be much lower, this will be even lower actually, this will be even lower value. So overall, initially the torque value will go somewhat below, because the fifth harmonic will be higher than the seventh one, so somewhat it will be in the lower side. Resultant, like this is the fundamental, somewhat the resultant will be on the lower side. Then as we move along, basically the fifth harmonic and the fundamental will slightly increase, so the value will increase basically, and somewhere here only I will receive the peak, right? And then this value is again increasing in the negative direction, so somewhere the value will reduce. Okay, here somewhat it will reduce, like basically graph, right? Graph will be somewhat like this, it will reduce because here then it is increasing in the negative direction, then again it is going towards 0, so the negative value is going towards 0 and this is increasing, right? So it will be something like this. Okay, so the graph, right, actually won't be purely smooth, that is the problem. Graph basically won't be purely smooth. Okay, so due to that there can be problems in stability. If you see it, there are like 4 points while it is touching, so there can be stability problems. So that is what it was telling, pulsating heating, right, can be happening, or the motor can locked in this problem, because if these harmonics were not there, motor is supposed to be in this position for stability, right? Now some, it can be in this position, it can be in this position, whichever position, I don't know. So there can be pulsations and heating due to harmonics. Okay, so yeah, that is the case. Okay, that is the case over here. So this is the problem with time harmonics. Now let's discuss about space harmonics. So we will go through this quickly because I don't want to waste much time. So basically this is the mmf for the phase A. For the phase B, right, same mmf will be there, just it will be phase shifted by 120. Why? Because the coils are placed somewhat like this. So this will be my, let's say this is my coil B, this is my coil C, right? Coil B, coil A, coil C. So coil B is 120 degree in the clockwise, so it is minus 120. Okay, so remember this current does not have any harmonics. So this current, right, basically I have just replaced I with Im sin omega t for the phase A. For the phase B I have replaced. So what is the current for the phase B? This is current for the phase A. For the phase B it will be Im sin omega t minus 120. Okay, this will be IC sin Im sin omega t plus 120. Okay, so basically that is what I am replacing over here. This is omega t, Im sin omega t minus 120, Im sin omega t plus 120. Current is fine, current, there is no harmonics in current, but in the flux distribution in the space there is harmonics. So there was alpha plus 120, there was alpha minus 120 alpha initially when we had derived the expression for resultant mmf, right? This was the value of the resultant mmf. But now what is happening, due to the harmonics, so 3 alpha component is coming, 5 alpha component is coming. Here what is happening, 3 times alpha minus 120, right? Because it is space displaced by minus 120. So this will be minus 360, this will be plus 360. So hence the third harmonic, right, there is no phase displacement for the third harmonic. For the first fundamental, it is minus 120 here, sorry, it is 0, minus 1, minus 120 here and plus 120 here. So that is what is written over here. For the fifth harmonic, you do the same manipulation just like the current one. current harmonics, time harmonics, right, you will see that it is providing a phase shift of for the fifth harmonic. You will see that here I have a phase shift of minus 600, that is plus 120, so hence it is plus 120, and this will provide a phase shift of plus 600, that will be minus 120. So actually what is happening is I am getting a phase shift in somewhat like a opposite phase sequence, right? So this is 0 plus 120 minus 120, and this is in the same phase sequence, 0 minus 120 plus 120. Okay, 0 plus 120 minus 120, 0 minus 120 plus 120. Okay, so yeah, this is the fundamental component, this is the fifth space component. Now we have the seventh space harmonic, right? Seventh space harmonic. So in the seventh space harmonic, what is happening, you will do the same calculation. You will observe that it is providing a phase shift of minus 120 for the phase B and plus 120. Do the same calculation. So basically what is happening is the fifth harmonic is generating a rotating magnetic field which is opposite to the fundamental. So this will be negative and this will be positive, because this will be in the same direction as the fundamental. Same, ditto, same, just like time harmonics, right? But here what is happening, what is the speed now? How can you identify the speed? So if you remember, this used to come, right? This was the like value where I would have easily told you that the speed, right, alpha is equals to omega t. So from here I can directly say that basically the speed at which my alpha will rotate will depend on omega. Here what is the speed? So here my 5 alpha is equals to minus omega t. 5 alpha equals to minus omega t. So alpha is equals to minus omega t by 5. So speed has reduced by 5. Speed has reduced by 5. That is the difference in space harmonic and time harmonic. In time harmonic, speed became 5 times the previous one. In space harmonic, speed will be reduced by 5. Okay. So yeah, that is what will happen here. So what I can say is speed is getting reduced by 5. What does it mean? So what is ns equals to? Ns equals to 120 f by p. So f, right, f is supply frequency. It is not changing, right, because supply does not have any harmonics. That is what we discussed. So what will change? Basically what will happen, the windings will develop a rotating magnetic field such that it has poles multiple of p, right? For fifth harmonic, what is happening to the speed? Speed is becoming ns by 5. Speed is becoming ns by 5. So if speed is becoming ns by 5, speed is becoming ns by 5, that means what? That basically means that this will be 1 by 5. So it is 120 f by 5p. So effectively your number of poles is becoming a multiple. So your number of poles becomes n into p for nth harmonic. Okay, this thing you have to understand. This is important in case of space harmonic. Your number of poles become multiple of the number of harmonics. Okay, this is one thing. And another thing is it is generating a torque in the opposite direction. Why? Because it is the magnetic field is rotating in the opposite direction. So again, the rotor magnetic field will try to follow the stator magnetic field, hence the torque will be generated in the opposite direction for fifth harmonic, same as the time harmonics. For seventh harmonic, it will be in the same direction. Okay, these are few things. One more thing is there. What is the slip? So slip in normal operation, S is equals to ns minus nr divided by ns. So from here I can find out one ratio. What is the ratio? Ratio is equals to 1 minus nr by ns. Okay, so from here I can find out my nr by ns, that is equals to 1 minus s. Okay, this is one thing that I can, anyways I knew that, right? Nr equals to 1 minus s into ns. So what will happen in the fifth harmonic? What will be the slip? So remember, because I want to find out the frequency of the induced EMF for the fifth harmonic, it will be slip s fifth harmonic into f, right? So basically, what will be the slip? Again, remember what is slip? Slip is the relative speed upon the synchronous speed. So what is the relative speed? Remember, nr will not change. Rotor will rotate with nr speed only, correct? But if you observe, I told you, right, the speed is getting reduced by 5, and remember it is in the opposite direction for the fifth harmonic. So that's why it will be minus ns by 5 divided by ns, minus ns by 5. Okay. So what I can say is my slip, right, S5 will become basically 1, minus sign will go away, plus 5 into nr upon ns, and nr upon ns is 1 minus s, so it will be 6 minus 5s. So basically what is happening, the slip, right, is getting opposite. So previously if my slip, somewhat, if previously my slip was s, now for the fifth harmonic the slip is becoming 6 minus 5s. What does it mean physically? So what will be the frequency? Frequency will be this only. Frequency of the induced EMF for the fifth harmonic in the rotor side will be 6 minus 5s into f. Okay. So what I can say, what I can comment is that basically previously if your slip was s, now it is becoming somewhat like 1 minus s, right? So the graph will be reversed. So previously if your torque speed characteristics was like this, now your torque speed, so this is not exact replica, so it will be somewhat like this, right? So now your torque speed characteristics will just be mirror image about the y-axis. So it will be somewhat like this. It will start from here, it will start from here, end at here. Okay. So this is the torque speed characteristics for 1 minus s, right? Because if you remember, if this is the graph of s, here the slip was 1, here the slip was 0. So but your slip has changed to 1 minus s, negative sign. Negative sign basically means it will be flipped. One more thing, the torque will be acting in the opposite direction, right? This we discussed, torque will be acting in the opposite direction. So basically your actual graph will be somewhat down here. That is what your actual graph will look like. Okay, I hope you have understood this point. Okay. One more thing, your, like this graph was drawn with a speed ns, right? If this graph was drawn with a speed ns, like this is the torque speed characteristics. This graph was drawn with a speed ns, but your speed has reduced. If your speed has reduced, basically this graph will be shifted downwards, more downwards. So it will look somewhat like this. Why? Because the speed has reduced. Okay, that's why the graph will be shifted more downwards, ns by 5, because the torque generated also will be lower. Why? Because of course with increase in harmonics, this you will learn in Fourier series, the amplitude will also keep on reducing, right? Here you see a factor of 1 by 5, here you see a factor of 1 by 7, right? Amplitude also will keep on reducing. That's why we generally neglect harmonic, because the amplitude itself is reducing. So yes, a opposing torque will be developed, but the amplitude will be much lower. Okay, understood? So these is the summary basically about the space harmonics. So basically here the space harmonics can be caused due to slotting. So basically if I show you right here, the way I am keeping my conductors, if there is some problem with slotting, then those harmonics will be present, because it is a mechanical thing, right? Saturation of the core, non-uniform air gap is not uniform here. So here the air gap is same, here the air gap may be more, here it is lower. So if it keeps on changing, then we will have this problem. Then winding distribution error. So how am I placing the windings? Due to those, some errors can come. Okay, so this harmonics distort the flux density waveform in space, not time. Okay, so yeah, So these harmonics distort the flux density waveform in space, not time. So yeah, they will distort the flux density waveform, but in space, not in time. Okay. So if P is the number of poles, then due to space harmonics, it can generate Rp number of poles depending on the Rth harmonic. Okay. So yeah, same thing is written over here. The speed will be ns, speed will become ns by 3, and the poles will become 3p. Okay, for the third harmonic and so on, right? So yeah, the effect, right? What is the effect basically? So let me first keep this side only because that is already done. So basically, in case of space harmonic, what will happen? We will have two kinds of harmonic. Okay, one is the harmonic induction torque, that is the asynchronous one. So basically, I don't have the torque speed. Okay, I have the torque speed graph. So this is the torque speed graph due to all the harmonics considered. So what will happen in reality? What will happen is that if I show you that overall what will be the resultant torque developed. So the resultant torque developed here, it is somewhat positive, here it is negative. So what is happening? This negative is lower, this positive is higher. So initially the torque will increase somewhat. Okay, initially the torque will increase somewhat. Then if the torque increases somewhat, then what happens? Then I see a sharp decline of this, right? So initially it is increasing, then it is reducing, this value is reducing, and this is still negative, right? This is still constant. So somewhat it will reduce, and it will cross the initial point because this is somewhat stable here, right? So I'm just adding the three graphs, that's it. Okay, so then what is happening is, then it is reducing, so it is reducing, but then my actual torque, right, fundamental torque is increasing by a lot. So this will dominate now, so again it will increase. Okay, increase, and it will basically follow this graph. Now the thing is that at higher speeds this will not be evident because the torque is present at lower speed only, the harmonic torques, right? So if load torque is here, no problem, but what if your load torque is here? Then there will be problem. What will be the problem? So here, right, suddenly if one of these points are stable, so my motor will lock. Here. My motor can lock here, right? So what will happen? The instant that my motor speed will increase slightly, it will reach here and it will feel like it's a stable point, right? So it is becoming stable at low speed. So basically what is happening, my motor is not reaching high speed. So basically it is becoming stable at low speed. Basically it is crawling. This phenomena is known as crawling. Okay, so crawling means it is crawling in this slow region only, like any animal crawls, right? Or we crawl. So it is crawling here only, it is not reaching the full speed. So due to harmonics, this can be the problems that can arise. Okay, if these harmonics were not present, then smoothly this was the stable point and my motor would have settled here. But due to that, basically this harmonics will push the rotor, basically will pull it here in this points. So how can I solve it? How can I solve this problem? So this problem can be solved by pushing the rotor. So if I push the rotor from this point, let's say it has stabled here, right? And at this point, if I push the rotor, right, push the rotor, then basically if I push the rotor, then basically yeah, then basically what I can say, then it will move out of this zone, and again, like if I push this, right, to, if I, like, let's say I'm pushing it, so I'm just increasing the speed slightly here, right, slightly. What will happen, then again it will move out of the stability zone and it will go, increase, and it will reach here. Okay, so it will reach. So if I push the rotor, then that is fixed. Or otherwise, what we can do, second option is provide high voltage. That is not possible actually, provide high voltage. Why? If I provide high voltage, what will happen? Then this whole graph, right, will shift upwards, because my torque is proportional to V square. Torque is proportional to V square. So if torque is proportional to V square, basically what will happen? The torque speed graph, developed torque speed graph, will move upwards. If it was initially here, it will move upwards. So basically my torque is here, right? So basically there will not be any possibility of crawling, because it will never intersect the graph at starting. Okay, so there will be no intersection point. At starting. So that is the advantage if I give high voltage, but that is practically not possible, because motor can get damaged, because it is rated at some voltage only, right? So this is how I can solve the crawling problem. So these kind of problems actually happen. Okay, and what is cogging? Cogging is known as magnetic locking. So basically what happens, I will just give you the theory, because that is only important, other things are not important. Okay, so this region, right, this region actually is called as the saddle region. Okay, I might do one thing, I might take this picture to the other page, that will be helpful actually. This region is known as the what do you call, the saddle region. Okay, so yeah, so this is what happens in this region. There can be, like, this phenomena is known as crawling. So another phenomena due to space harmonics is known as cogging. Cogging means the motor will not start, motor fails to start at all. Why? Because what happens, if the slots on the stator side and the rotor side are exactly same, or integral numbers. Okay, if they are integral numbers, I will discuss about that. Then what will happen, whatever magnetic field it will generate, that same instant the rotor also will generate the same magnetic field. So both of them already are stationary to each other. So if they are stationary to each other, they are already aligned, so there will not be any torque generated. Okay, that is what is written over here. So starting issue is observed mainly in squirrel cage induction motor, where the motor fails to start due to locking between the stator teeth and the rotor teeth. Okay, so this happens when the slots are integer multiple of each other. So basically if S is equals to some ms2, then right, there can be problem of magnetic locking, or S1 minus S2 is some integer, then also there will be problem. So I have written over here. So, or sorry, it is not, S1 minus S2 is not equal to the number of poles or integer multiple of poles. Okay, so just theoretically I am explaining it. Okay, I am not explaining it like numerically, because that is not important. So if stator as standstill, if stator and rotor slots are perfectly aligned to each other, the magnetic circuit reluctance is minimum, which favors the flux linkage. So flux is already linked between the stator and rotor. As the rotor attempts to move, the reluctance increases due to misalignment between the magnetic fields. Okay, like basically initially the reluctance was minimum, so the flux was linking. Now as soon as it tries to move, the reluctance became very high due to non-linkage, and due to that what happens is that it is not able to rotate properly. Okay, due to that reluctance, a reluctance torque is generated that will oppose the developed torque, magnetizing torque that the stator wants to develop. Due to that, the motor will fail to start, and this generally is seen on the low starting torque motors. Okay, so avoid multiple stator and rotor slots which are like integer multiple of each other, right? Or the stator and rotor slots are subtraction of them is equals to an integer multiple of poles. So these two things you have to avoid anyhow. Okay, we can skew the rotor slot. Skewing basically means what we can do, right? This generally is evidently present in the squirrel cage. So in squirrel cage, how is the rotor bars? Rotor bars are like this, right? So what we'll do, initially we will try to intentionally provide some angle difference with skewing between the flux lines. So we provide the rotor bars in angular difference. Angular difference, what happens, then the flux will cut in angle difference. If there is angle difference, then what will happen, then torque will be generated. Okay, so that is how I can prevent initially starting. If I provide a phase difference, like skewing basically means providing the, if the rotor bars are like this, right, straight, so I will provide them like this, connect them like this. So there is, like, initially there can be less flux cut here, but here there will be more flux cut because there is angular difference. Okay, that is the only reason. So, or we can use distributed windings. So distributed windings is like that can smoothen out the air gap flux density, due to which reluctance will not be an issue. So then if the rotor tries to rotate, it will not receive the reluctance torque. Okay, just remember this thing. I'm explaining this theoretically because only this much is important, other things are not important. Okay, crawling I have already explained how does crawling happens. So this is how you can prevent. Use proper slot combinations for cogging. Applying skewing also can help prevent. So this is how we skew, right? So basically you skew basically means it is with the angle. So normally the rotor bars will be straight, but it is skewed with angle, so there will be flux cut. So that is how it will provide the initial starting torque, because there can be problems with the initial starting torque. Okay, and yeah, I hope you have understood. Now let's do one basic question and let's wrap this lecture up. So a 3-phase 50 hertz square wave VSI speeds a 3-phase 4-pole induction machine. So a voltage source inverter is speeding a induction machine. What does it mean? So it is a square wave, right? Square wave basically means the voltage waveform will not be purely sinusoidal, it will be a square waveform, something like this. So you will study this in inverter. So actually we can never generate purely sinusoidal waveforms with inverters, right? That is not possible, but we can optimize it. Okay, so it is a 50 hertz, okay, 4-pole induction machine. So what kind of harmonics is this? Time harmonics, because now the harmonics are in the voltage supply. The VSI line voltage has a dominant fifth harmonic component. So it has a dominant fifth harmonic component. Okay, fine. So basically that fifth harmonic component will have a speed of 5 ns. Okay, that is fine. If the operating slip of the motor with respect to fundamental component is 0.05, so normal slip, right, S equals to 0.04, the slip of the motor with respect to the fifth harmonic component will be what? So we know that the synchronous speed of the fifth harmonic component will be 5 ns, right? That is what we know. It is time harmonic. So they are asking me what will be the slip with respect to the fifth harmonic. So what is the speed, rotor speed? It is 1 minus s into ns. So this will be 0.96 into ns, that is so what is ns? Ns is 120 f by p, 122 into f, that is 50 by p, p is 4, so this will be 30 into 50.96, right, 0.96. So 0.96 into 1500, 1440. So NR is 1440. So what is the slip for the fifth harmonic? So basically it will be the new ns. And remember, what does the fifth harmonic do? So fifth harmonic, if you remember, it rotates in the opposite direction. So only this much information is required to you. This kind of questions will be asked. Rotates in opposite direction. Fifth harmonic always rotates in opposite direction. So what will be the relative speed? Relative speed will be minus of 5ns minus of nr divided by minus of 5ns. Okay, so it will be basically equals to 1 plus nr by ns, 1 by 5 into nr by ns. Nr by ns is 1 minus s, right? So this will be 1 plus 1 by s, that is okay. Anyways, we did not require the that value, right? We did not require actually nr actually. Okay, this will be 0.96. So this will come out, I will calculate this value. So 0.96 divided by 5 plus 1, so 1.192. Okay, this will be the slip of the fifth harmonic, and as I can observe that the slip of the fifth harmonic is greater than 1. That means what? That means it is rotating in the opposite direction, because if you remember, the graph was something like this. This region was the motoring region where the slip was between 0 to 1. This region was the region where the slip was greater than 1, right? Sorry, no, here the slip was, yeah, this was the region where the slip was greater than 1, and here the slip was basically negative. Slip negative meaning my nr is higher than the ns. Okay, so yeah, I hope you have understood this point. So this answer will be 1.192. This will be the answer of this question. So don't worry, in harmonics simple question only will come, nothing fancy will come. Okay, so whatever I have told you, that much you have to understand theoretically. Other things are there are so many things, but we have to cover the syllabus. You are a GATE aspirant, right? You cannot do everything right now. So yeah, just do whatever I am saying, and that much should be sufficient. Thank you for watching, and I will see you in the next lecture, because this is the end of the induction motors. In the next lecture onwards, either we'll start with single phase motors or with synchronous machines. Thank you, and I will see you in the next lecture. Until then, happy learning.